Here is a formal description of this problem, but this diagram makes things, I feel, clearer. So we have a grid, right, represented here, and the numbers represent the direction that these obstacles are facing. So -1 means it's facing to the left like this, 1 means it's to the right, -1 means the same, parallel to this, the same, and the same thing as you can see there. And what we want to return is whether or not a ball dropped in either one of these columns makes it to the end. And if it does make it to the end, what column made it to the end through. So in this case, it's not going to make it to the end. It's going to be stuck at the wall here and here. So we return -1, -1, as you can see. And in this case, we have this grid described here, right, which leads to these blue lines. And what happens is as you can see here, it would get stuck on the wall here, but in this case, it will go and come out through here. So it went in through this, and let's say they're indexed from 0, so 0, 1. It went in through 1, so that the 1th index is going to have 1 in there. That's why it has 1 in there. And this is going to be -1 because the thing that came in at the 0th index didn't make it to the end. Now in this example, right, if you pay attention to it, the grid is described here, right? V's also stop things from making it to the end. So we have 0. Once that 0 came out through 0, so we have 0 here instead of -1. The thing that entered the second column, with the 1th column, right, if you were counting from 0, came out through the 3rd, if you're indexed at 0, the 3rd outlet over here at the bottom, and the rest didn't make it. The last 2 didn't make it, so -1, -1. I hope that's clear. And here's just one more huge example, but it's pretty much the same thing. Now for the solution to this problem, we initialize the result array with -1 and start dropping the first ball from the first column. And so it starts off a -1, right? And in the very first row, it gets stuck because there's a left border of the grid. So move on to the right. What does that look like in code? Everything you need fits in here, which is encouraging, right, for a medium problem. So first of all, we initialize the results array, fetch the columns, set everything to -1. That's what this does. Next, we're going to loop through each column in the grid. So that's what this logic does. And what do we do when we're looping through each of the columns? In each of those loops, we're going to loop through each row as well, as you can see here. So I'm just trying to lay out the solution to this problem. Now within each loop through the column, we get the current column here. Then we loop through each row in the grid. But first, this is crucial, getting the next column, because that's what we check whether it's going to make it or not. So if the next column, based on the shape of the grid, remember we're passing the grid and that determines the shape of the obstacles, the direction they face. Based on the direction it faces, you add it to the current column. And if we wind up in these failure modes, we break. And we know that that column is just not going to make it. And therefore, its slot in the result is going to stay as -1. Okay? So if it's less than 0, like in this case, this would be less than 0 because it was hitting into the wall at this edge, right? It's not going to make it, break. If it's more, right, that's if it falls to the right, in this case it doesn't, but if it did, then it's going to fail as well. Or if it forms a V, so if it forms a V like this, right, if it forms a V like that, which is going to be represented by the direction here not equaling the direction right after it, break. Otherwise, if you made it this far, might as well check, if we've reached the bottom. So if the row is at the last, the row will manage to make it all the way to the end. So we're going row by row here, right? And if you manage to make it to the end, set that particular column, right, wherever it came in through, set it to what we put, to what is the new next column, right? So that would be where it wound up at. and then set the current column to the next column. And so we set it after the fact, right? But this is for the case where this we've not already been there. I don't see why they would add this. This wouldn't always be useful. Basically, it's useful when we're evaluating every single row, right? But if we've gotten to the end, right, then this loop is going to terminate anyway. So this is going to be reset again up here outside. So this is being set for within this for loop right here, not for this outer one. Okay, because once this branch triggers, it means this inner loop is done, right? So then this is going to be reset. So this is what helps us move on to the next column for the same ball, right? To set the next column for the exact same ball that started in the beginning, to keep track of where it's at. That's what this does. And I hope this makes sense. Feel free to use a debugger, right? Step through this diagram, other examples of this diagram, right? So you can see, right? Because we need to know where it was, right? Row by row, the current column, because it doesn't always end up where it starts, right? And that's what's being updated here. Okay, that's all. That's all there is to this problem. Time complexity, same old, n by n. Space complexity, same old, O1. Like, comment, subscribe if this was useful to you. Share, upvote. See you next time.